Everybody, welcome to Power and Efficiency. So this is still part of our unit on work, energy, and momentum. And power, we tend to use work, energy, and power synonymously. That's not quite the way it should be. So first off, we know that power is the rate of doing work. And that's important because when we have the rate of something, there's typically a time unit involved, and we know how to solve for work. So the first equation that we're going to use is pretty simple. It's just work divided by time. That's for power. The units on this, they're pretty straightforward. This is a joule per second, energy per second, or a watt. We use a capital W, so you'll see kilowatts and megawatts and all that stuff. So the unit for that is a joule per second or a watt. Another way to think of power is a change in energy per unit time. And so most often we see like a change in kinetic energy, a change in potential energy somehow. But work, we remember, is force times distance. So we have these multiple ways to find work when we're talking about power. And then we just simply divide it by time to get the power done. All right, so here we have a pretty straightforward. We have a physics student setting up a body slam on a poor biology student. So we know the person is lifted, the 75 kilogram student is lifted clear over the head to a height of 2.2 meters. There's a time involved. How much power did the physics student generate? So the power is pretty straightforward. It's work divided by time. If we know work is force times distance, FD over T, and the force, so when we have these kinds of problems, we're going to assume the person was lifted at a constant velocity. So the force that was used to lift the person was their weight, or their mg. The distance is that height. Then we're given the time. So this one, we pretty much just straight plug and chug on this one. That should be 9.8 and 2.2. The time was 0.675 seconds. So we get about 2,400 watts worth of power the student generated, or 2.4 kilowatts of power that the physics student generated. Okay, so that one's pretty straightforward. Once again, real quick, at a constant velocity, the applied force F is equal to the mg, so that is why we used mg in that chunk right there, just to make sure we remember that. Okay, so for, next example is we have the change in energy way to think about this. And the reason we know it's the change in energy method is we have an initial velocity here and then a final velocity. And that's going to be the best way to think about this one, the most straightforward way, I guess. So if power is a change in energy over time, once again, that is work. Specifically, it is the change in kinetic energy over time. So there's a couple different ways to do this. I'll kind of set it up like this. It's 1/2 mvf squared minus 1/2 mv naught squared all over time. And then we just do a little bit of math on the top to clean that up, just in case you see some solutions that look like this. That's what that turns into. So power looks like this. So power is equal to 1/2 the mass of 850 times that change in velocity, so the 12 squared minus the 4 squared, over the time interval of 4.5 seconds. And we get about 12,000 watts, or about 12 kilowatts of energy the engine produced. And once again, we ignored friction here, so we didn't take into account the energy lost due to friction. So we used a physics land motor there, okay? So that's the two ways we think about power using work and the change in energy method. There's another pretty useful equation for power. Based on the units, if power is work divided by time, power is force times distance over time. And we see this distance per time thing here. So the other way we can think about power is the force applied, or the force that's doing the work, times the velocity. A little caveat here. This equation only works for constant velocity. So if something changes velocity, it's a little more difficult to manage. So only for a constant velocity would this thing work. So an application of this kind of problem looks something like this. A student is pushing 14 kilograms of their physics homework up a 40-degree ramp at a constant velocity. The friction force is given. How much power must the student exert? All right, so we have to remember our way to set up a ramp. So here's my ramp. Let's call this FG down here. My normal force will be pointing this way. Looks like friction is FG parallel, and then friction is pointing up the ramp. I'm sorry, down the ramp is that component of weight. We know this is going to be mg sine theta, right? Because my angle is going to be right here. And it looks like that's about it. If I understand it this way, power is the applied force times velocity. Well, that force that we're going to be dealing with is the parallel chunk down the ramp plus friction pointing up the ramp times the velocity of the thing. And then we go through and solve for all the pieces. And when we plug all of our numbers in, it's 14 times 9.8 times sine of 40 plus the 26. So once again, this 26 newtons, that's how much friction is already pushing up the ramp. We're given that information. That should be multiplied there. Times 3.2. So here, the power to push this up this particular ramp is 365 watts. Okay, so that is generally how we do these kinds of questions.